Hello. So, the guy that was meant to take this session is not here. So I am standing on his behalf. Okay. I'll try as much as I can to explain this non-trivial area of technology. So, but how many of you here are conversant or have heard the word quantum computation before? Just if you've heard oh, very few. Wow, okay. So many of you here will think of it as things that physicists do, right? Because of the word quantum, right? Naturally, that's what we think. Quantum. Okay, so I'll be talking to you today about quantum computation. I'll try as much as I can because it's not something quite easy to explain, but I'll bring it to light. So I will tell you about, I would tell you what quantum computation means and its application to industrial optimization problems. So my name is Afam Madu. I am a startup incubation manager at Rural Hub and also a quantum guy. But remember, at the beginning of this conversation, I told you that the person that is meant to take this session is not here. Okay? So, next. Yeah, we are familiar with this guy, right? This is about Einstein. Now, Albert Einstein is known for a couple of these and more. Of course, and more. So, photoelectric effect. If not for photoelectric effect, today we would not have solar panels. Of course, right? So, if not for photoelectric effect, there will be nothing like solar panels. So, I wouldn't want to start telling you about photoelectric effect or maybe trying to break it down. It's something that you could always find on the internet. So if not for his general theory of relativity, we're heading to somewhere with this. I wouldn't come here and start telling you about quantum computation all of a sudden. You will miss it out instantly. So if not for his theory of relativity, our GPS wouldn't be as accurate as it is today. And then if not for his innovation in quantum theory and the rest, wouldn't have miniaturized electronics just as you are flexing your phone now. So this guy I see here is not a mere human. If there was anything like, I don't know if the word genius if we could describe him more. You know, after his death, his brain was splitted in so many cities to understand how could someone have such mind. You know, he never did a single experiment. All his experiments were thought experiments with his goof. I don't know, should I call it goof? That's when he sips. You know, so he's not, I don't know, let's not go into describing Einstein's mind. So, but I have a reason for putting this quote here. He said this, not me. He said that I see a time when technology will surpass human interaction, that he bets that it will be a world of idiots. But come to think of it, these days we are all glued to our phones, and Facebook is trying to put us in a virtual environment forever. Of course, right? So, I don't know, this young man looks like a soothsayer. He sees the future. So, with time, technology will reduce our interactions. We wouldn't have to be here again. That first might get to a time where we wouldn't have to be here physically. We could actually attend it virtually if the possibility, if there's a possibility for such implementation at that level. So that's like an illustration, or should I say a definition of what this quote is saying. So next, please. So even in his whole intelligence and intellectual, he never believed in quantum mechanics. He saw quantum mechanics as something. He wrote this letter to a friend. Oh, it's not clear. He wrote this letter to a friend, doubting quantum theory. This same theory that is responsible for electronics is responsible for a lot of things that you know today. It is this same theory that explained. It is quantum theory is the most complete explanation of the universe as you know it. I'm not here to tell you anything about physics, okay? But quantum theory is the most generalized theory of every physical object or of anything in the universe. I mean, it is a theory that completely generalizes everything at all. So, but this same guy with his whole intellect doubted it, never believed, till he went to his late grave, not early grave. He never believed in it. He never, not that he didn't understand it. He doubted everything that it says. We know of the famous spooky. How many of you have heard of spooky effect at distance, entanglement? Wow, these things are quite odd for you guys. Okay, no problems. Look at what entanglement is. It looks magical. Entanglement is simply trying to say that if I have a particle here or an object here, okay, and I have another object here, that if I do something to this object, that it would influence the behavior of this object here, even though they are separated. That's what physicists are telling us, crazy people. That objects could influence themselves at spatial distance. This thing might look like, you guys are looking at me like you're not even having a clue of what I'm saying. I should go on. I have to be sure you're understanding me. You're digesting. Einstein, when he presented his paper in 1905, he had almost, he was a very young guy. He had almost an audience that could fill the whole place. Nobody understood what he was saying, but they were all nodding. But nobody understood what he was saying, but they were all clapping, nodding. So I want to make sure that history is not repeating. I'm not Einstein anyway. So what I'm trying to say here is, what I'm trying to introduce here is, back in the 1990s, before the advent of web, www, I don't know how things were then, but we never had anything like internet. Think of the time when there was no phone, when there was no way you could contact someone, just like you could easily use your WhatsApp now and probably put up a video call or something. And a paradigm of computation is coming, just as web was disruptive during its time. This paradigm of computation is not clear to everyone now. It looks so vague, but when it opens up, it's gonna take us by surprise. How do I put this? Researchers are working on how to use this silly thing I described, entanglement, to perform computation, to build a computer. Okay? So that is where I'm trying to drive us to. Next slide. Hello? Next slide, please. So, I don't know if this could help us develop some sense of understanding. So if you want to understand the secret of the universe, don't misunderstand the terminology universe. And we are talking about everything. Think in terms of energy, frequency, and vibrations. Now, let's start with energy. Very, very, very illustrative. We are all sitting here because we have energy in us. When you eat, it digests. The digestive organ generates energy to keep you, active, working. Okay? So, we're having this global issue today because we are disrupting the energy of the earth. We are increasing the thermodynamic energy of this planet. We are killing this planet. We are like virus on earth. Killing this planet by increasing the thermodynamic energy. So energy is responsible for everything as much as you know it. Frequency, one could place an EEG now on your brain and predict if you're going to be having Alzheimer's or dementia, or one could use such same gadgets to tell if you have good sleep or not. The same thing with vibrations. This building is vibrating. If you want to understand anything at all, I don't know, you guys are developers. Well, I'm a physicist. So, but if you want to understand anything at all, if it becomes difficult, think it through these things. Think of anything at all. So, this was said by Nikola Tesla, but you understand where, as this slide proceeds, you understand where we are heading with this. Next slide, please. One silly thing with quantum computation is it's non-trivial, so it's actually quite difficult to explain. But what we observe is not nature itself, but nature is exposed to our method of questioning. Now, I don't know your names. I don't know I don't know what you like until when I ask. You can't tell anything. You cannot be specific about anything. There is no certainty in this universe. All you have is a chaotic environment filled with uncertainties until when you ask a question, until when you try to measure. So that is just what this statement is trying to say, that it's only when you try to measure something that you get an information from that particular system. So let me take you guys back to, we all know that light, as we know it, light, this light you're seeing here, was thought as a wave during the time of Isaac Newton. Light could be reflected, it could be refracted, it could be interfered. That was just because of how they were measuring it. And I don't know how many of you there must have heard of light particle duality. So that was just because of how they were measuring that same light that in the Bible they said, "Let there be light." So that same light, that was just because of how they were measuring it. So, but when during the time of Einstein, we discovered that this same light that exhibits wave properties could still exhibit particle properties, could still have particle properties. What are those particle properties? This same light could knock out electrons from a metal. The same light. So it depends on how you ask, how you measure. It boils down to how do you want to investigate this system or this system. So is it that your brain is influencing the thing you are measuring, or the universe is influencing it? I'm not here to twist your mind anyway, but this young man said that his mind is already twisted. I'm not here to twist the mind, I'm sorry. But if you want to take it a little bit deep, what's influencing which? Is it that your brain is influencing what you're measuring, or the environment is influencing what you're measuring. Okay, let's continue. Let's go to the next slide. Now, this was the first guy that introduced the idea of quantum computation. This is Richard Feynman. If you have your Google here, you can check it out. This was the first guy that thought of, could we actually build a quantum computer? So this brings us to, what can a quantum computer actually do? And what can it be capable of if it becomes mainstream? This young man here is not going to be having a quantum computer. You're not going to be carrying a quantum computer like this in the nearest future. But if it becomes a dream that comes to life, what is he going to be doing? This is the first person that asked the question. So he said, the physical world is quantum mechanical. And what is the possibility that there is to be an exact simulation? Okay, if I tell you guys here now to simulate, or let me say, to simulate this program backwards. Do you know what I mean by backwards? From here, simulate this program to when it started. How did this program start? This particular day first is an event. So it means that some of us here that are familiar with machine learning and deep learning understands that you can actually predict make a prediction of something if you have a complete information or data about that thing. So think along with me. Do you think this event can be simulated backwards? Oh my God. I think I've lost my audience. No, but come on, let's do some thinking here. What I mean by simulating it backwards, I'm not trying to say that you'll be trying to rewind it, but can you completely describe this event with a computer program from what you are experiencing now to when it started? Can you completely describe every single moment without losing an information of what happened? You can't, because you're going to be simulating it with a classical computer. You cannot. Sorry. Okay. Good question. Did he hear what he asked? He said, when you talk about when I talk about simulating this event, am I trying to say simulating every individual action or simulating the general action, the general thing? Good question. If you're going to be describing this event, you should simulate even a time when someone did like this. Can you give me your pen, or what's your name? You would be that descriptive. It's not possible, right? But physicists are telling us that they could build a computer that can do that kind of computation. A computer that can distinctively describe any system you want to define to it. So Feynman was the first guy that asked that question: can we build a quantum computer? Well, quantum computer might not be mainstream to you guys now, because it doesn't come to mind in Africa. I don't know why, but when it finally gets here, it's going to look like a surprise. Wow, oh, there's a computer that can do this now. So, next slide, please. Now, this brings us to Moore's law. I don't know how many people here are familiar with Moore's law. Moore's law. How many people here are familiar with Moore's law? Okay, I believe is it that you're an engineering student, or you are an engineering student? Oh, of course, okay. Now, very simple, look at what Gordon Moore in 1965 was just trying to say. Moore was a co-founder of Intel. He was trying to state a theory that transistors, you know that computers make use of transistors to perform computation. I hope we are familiar with that. It is those how do I put this? Those information you get from your computer as a result of transistor switching using gates. So it's either it switch from 1 or 0. That's why below C, what you see in machine language is ones and zeros. So those ones and zeros are outcome of what transistors give you, like transistor switching. I don't want to start describing transistor switching here. But what Gordon Moore was trying to say is that transistors are going to get smaller and smaller and smaller for every 18 months. The integrated circuits are going to be, getting smaller. Miniaturization, that is what you call nanoscale, nanotechnology. So, but don't forget that these same transistors makes use of current and voltages in order to switch. And you know that current itself is the movement of electrons. Let me not bore you guys with the physics, but the bad news is that Moore's law is no longer, it's been defined as a 2006. Computers cannot get any smaller. Your integrated circuits cannot be further miniaturized. Why? The smaller they get, the closer the transistors get to each other, the more quantum mechanical they become. I mean, instead of miniaturizing a transistor, why not simply build a quantum computer? Since you cannot increase the clocking of a transistor, why not simply build a quantum computer? Like, people are here talking about Web 3.0. Some other persons are here talking about blockchain. Look at the revolution that is going to befall us. There will be a cloud-based quantum computer that will be able to handle distributed data on a blockchain platform through a fast internet, what you call seventh generation, fifth generation. All those things are like, those technologies are equally developing. So there is no way that computers would continue to be developed in this manner. If you're not following the news anyway, maybe look out check out the controversy between China and US. They're always on a war. Now they are currently on a war to express what they call quantum supremacy. The two countries are trying to, rub the shoulders on who has the best quantum a quantum computer. A computer that can actually do all these things I told you of in the previous slides. So, So this statement here, transistors are great, and electronics are, of course, electronics are the most advanced technology that man ever conceived. Without electronics, we will not even be here. Let me start out. This screen is not even going to be coming up without electronics. So that was such an innovation by man. But transistors cannot get any smaller anymore. They can't. I don't know if I'm making a point. They can't get any smaller. So it will be a waste of money trying to miniaturize a transistor in order to increase your clocking rate in your transistor. Why not just use that money, invest it in a quantum computer that will outperform a classical computer in no distant time? Like, I'm trying to show you that quantum computers are no longer in the lab. Quantum mechanics, if you've heard of quantum physics, they've left the laboratories. They are coming mainstream. Soon you're going to, okay, don't worry. Next slide. Let me don't ruin the font for you. I don't know why this guy put this here. Remember, I told you at the beginning of this conversation, I'm not the guy that's meant to present this. Okay? I told you I'm not the guy. So, I don't know. What is this? Like, of course, we all know what this is, right? What's this? Remember? Look well before you answer. No, but seriously, look well before you answer. It looks simple. Remember the slide that told us that it is only what you ask of nature that you get. Remember that slide? So, what is this? Please, I want someone to actually. It's very simple, but what the hell is this? Huh? Yeah? No, come on, throw the answer up, but just. Refrigerator, right? Could it be that easy? Anybody from here, what's this? Refrigerator. It's a refrigerator, right? Is it this? Toaster. Okay, it's a refrigerator. Come on, it's a refrigerator. This doesn't look like a chicken or something. This is a refrigerator. So, next slide. Remember, you called that one a refrigerator. So what's this one? Huh? Come on, you called it a refrigerator. What is this one? Huh? He said a chandelier. Wonderful. He called this thing a quantum computer. Whoa. I mean, you have the mind to call this a quantum computer. Wow. You guys are not responding. What is this? Huh? Can you be more audible? White seller. Great. So, well, next slide. Let's find out what it is. So that whole thing I've been telling you about quantum computer, this is what a quantum computer looks like. Yeah, it looks like your chandelier in your sitting room. This is what it looks like. Google has one. IBM has one. Microsoft has one. All these big tech companies, they have one, all of them. This is what it looks like. So, what is a quantum computer? It's a device that leverages on the specific properties described by quantum mechanics to perform computation. Please, next slide. But this is what a quantum computer looks like, okay? What are those specific properties? Now, first of all, we're familiar with beats, classical beats. Come on. And some of us who have heard of Schrodinger's cat. I don't know if anybody here has heard of Schrodinger's cat. A cat that is dead and alive, and at the same time, it's dead and is alive. But come to think of it, if there's a cat inside this thing that we're seeing here, can you categorically tell me from that distance that this cat is dead or alive without looking? It's only when you look you know. That's just simply what this picture is trying to mimic here. The smallest unit of computation in your computers you're having here is called a classical bit. But the unit of computation or information in quantum computer is called a qubit. So a qubit is just a direct replication of a qubit is this. You cannot actually say that it is in state 1 or state 0. It could be in any of those states at the same time. That is why it's going to be faster than your classical computers. It could be in any of those states at the same time until when you measure. I know that this thing looks like a movie to you, but next slide. I'm already being rushed. Well, I've never taken a class where I explained quantum computation under 30 minutes. You have to actually start from the history, 1900. climb to 1982. Like, you have to actually carry the audience, but I'm sorry. So, when an electron spin is manipulated with a magnetic device, a magnetic field, think of this as an electron, a single electron. We all know the electron have spin, either spin up or spin down. So, the craft behind quantum computation is, information is encoded in the spin of an electron. And you know that electrons spin very fast. They are very sporadic. That's how they generate momentum. They call it quantum. Momentum. So, encoding that information in such fast spin could easily perform computation faster than your switch, faster than your transistors. Just get the intuition. Towards the end, if you really want to get more of what this thing is all about, or how you can start learning about quantum computation, well, we can always find ourselves on any of the platforms. So please, go on. I'm not going to be explaining this. I'm sorry. I should try. It's not like I can't, but if I'm going to be explaining it, I have to be as explicit as possible. Okay. Superposition is a terminology that is used to imply the fact that a qubit can exist in two states at the same time means that they are superimposed. Superposition, being in two states at the same time. Entanglement, well, when there is a sustained superposition, then two qubits can actually be entangled. Wow. I can't believe I'm explaining this thing with this kind of... Please, next slide. Next slide. So, a rare picture of a qubit processor. This is what a qubit processor is. Not the diagram I showed you. The diagram I showed you is a geometrical representation of a single bit in a quantum computer. A single bit. So, but whatever Google and IBM and the rest have behind their quantum computers, this is what the processor looks like. So, I just wanted to show you the picture. Next slide. Yeah. A block sphere is a geometrical representation of a qubit. I won't lie to you guys. I didn't expect to have audience in this class. I'm not going to lie to you guys, because this thing is pretty technical. But it is not impossible to understand. You just have to spend time. So this is what a qubit looks like, and these are the gate operations. All you need to do to write these codes is just Python. I saw Python here. Yeah, this is a Python function, right? So all you need to do is just know how to code in Python, then develop the intuition, because all those things are your gates that you can use to switch this qubit into any state. Now, very simply, you have a three-dimensional space to encode information. While in your classical systems, you only encode information on, you see that you can only visualize, those of you that does machine learning, you can only do your visualization in 2D. You can't visualize in 3D in that screen. So this paradigm of computation gives you the ability to encode information in three-dimensional space. So there are patterns that your normal, if you're going to be doing quantum machine learning, there are patterns that your model can generate that your classical machine learning models cannot be able to show you, because machine learning is all about what? Getting information from data. I'm not here to tell you anything about machine learning anyway. So, next slide. I told you that I know that you guys are not understanding what I'm saying. I'm so sorry if you're not understanding, though. Okay. So with just 275 qubits, you can represent more states than the whole atoms in the whole universe. With only 275 qubits. What does it tell you? Is anyone thinking with me? That with only 275 qubits that you can represent the whole atom in the whole universe. Can we think of the atoms in the whole universe? Our universe is vast. We don't even know, we can't even quantify the total number of atoms in the universe. And with just 275 qubits, you can be able to express each and every one of the atoms. So we can simulate this event with 275 qubits. If we have sensors, motion sensors, camera sensors, every kind of sensors that will get us the information of what has been going on here for the past hours, how many hours that events has been going on. Use that in data to simulate this event. And simulating this event is actually a very simple thing to do. The truth. Next slide. Yeah. Are we going to be having, our quantum computers going to be replacing our conventional computers? No. You're not going to be having quantum laptops. Nah, you're not going to be doing that. You can only access them through the cloud. Next slide. So for those of us that think that they will be having that kind of chandelier thing in there, no, you're not going to be having that. So what class of problems can we solve with quantum computer? Well, if you are interested in quantum computation, this is what they code. They call it quantum circuits. This is what the circuit looks like when you're performing your computation. This is what it looks like, this. So you log into your laptop through the cloud. Of course, you should have an internet. You write your code. You send that particular circuit to their qubit processor. It depends on the system you're using, IBM, Google, whoever. You wait for when the computation is finished. You get your result. What is the relevance of a quantum computer then? Why do we need a quantum computer when we have a classical computer? See, the biggest problem in computation is timing. It takes a lot of time to perform a very big task. Like when I mean a very massive amount of tasks, and it takes a lot of space. So for those of you that knows about computational complexity, it takes a lot of time to finish a big task, and it's a lot of space too. So quantum computation, if we're in business, if we're all competitors, and I make use of quantum computer to consume the amount of data that allows me to generate information to make the next decision in my business, in my marketplace or in my business, and you make use of a classical computer. Look at what I'm going to be doing here. Within the shortest possible time, I'll beat you in the game. That's just what I'm trying to say. That within the shortest possible time, if I have the right computation and the right amount of data, I'll beat you in the game. Simple. That's just what I'm trying to. That is what I meant by what class of problems, because I wouldn't really spend time now telling you about combinatorial problems. So next one. Yeah, combinatorial problems. Every day of our life, all of us here experience combinatorial problems, but we don't know. For you to wake up in the morning to plan your day and determine how you want to have your day, that planning is already a combinatorics. Uber today makes use of a search algorithm to know the shortest route to follow in order to satisfy their customers. It's a combinatorial problem. The very familiar one, the traveling salesman problem. It's a search. Is a search problem. What I mean by search here is, let's assume that we are given a task to determine who is the fairest person here. No, I need a very big problem. Okay, what is the shortest distance from here to Kaduna State? Shortest distance. Can anybody do that computation for me? The shortest distance from here to Kaduna State, or the shortest distance from, that's when I mean, those are the kind of problems that a quantum computer will enable one solve. Why? These computers have the ability to encode information in in a superimposed state. Like instead of when your computer will be switching from one transistor a bit to the other, from bit 0 to bit 1, this guy can stay in both bits at the same time. So the more qubits you have, the more space you can cover. The less time it takes you to perform a task, the faster you are in getting your results. I don't know if you guys are getting the point now. So there are a lot of industrial combinatorial problems. Industries that are into manufacturing, large manufacturing industries, run into combinatorial problems every day. Pharmaceuticals run into combinatorial problems every day because the thing you hear about optimization is simply, how do I increase my profits, reduce the time it takes for me to perform a task? That is what a combinatorial problem is, or an optimization problem is trying to solve. Minimize or maximize, which is exactly what your cost function or your objective function in your machine learning algorithms are after. To optimize your model to perform better. So next one, please. Yeah. These are just a very few examples of combinatorial problems. Advanced manufacturing. Well, you'll be wondering. I wouldn't break it down, but I promise you, I have an article on this particular thing that could enable one who wants to go into it. You know, we are after the trendy tech thing now. People are entering Web 3.0, blockchain. Why? We are hustlers. Nigerians, we try. We are going after that thing that is mainstream. If you are there early, imagine people that started blockchain in 2000 and when? 2000 and when did it start? 9. Imagine someone that started learning about blockchain development in 2008. And now, come on now. The youngest Google GDE was once here. He started early. So it's all about what? Locating that particular niche that is still developing. Getting there early and becoming a developer there earlier. When it becomes mainstream, come on. Like, you know. So, yeah, I know you're about to come on. Yeah, I know. I know. Next one. So I must tell you the truth. I just scratched the surface. But I take classes on quantum computation. So if you're really interested in it, network with me. Because I lead an international community here in Nigeria on quantum computation. So if you're really interested in how it works, I'm open for networking or collaborations or anything at all to expand the knowledge and should I say education, because it's going to come. What's industrial revolution? Communication, transportation, and energy. Taking another turn. Revolution. So this guy is going to be bringing in computation. Your blockchain is going to be bringing in, I don't know, energy, solar. Okay, how many of you followed Glasgow, the UN event in Glasgow? They gave everybody ultimatum. By 2050, you shouldn't be using diesels again. 2050. Oh, and I heard some sad news that Lagos is going to be drowning in 20 years due to climate change. So the white guys are saying, by 2050, you shouldn't be making use of diesel, crude oil, nothing again. Get your hands off it. Make your electric vehicles and embrace green energy. So it's clear that this guy is going to take over the computation. So these are the level of just a few kind of problems that your combinatorial problems that quantum computations could solve. So you could just make a snapshot of it and then, please, next slide. Yeah, that guy is already angry at me. Yeah, recommendations for early adopters, okay? Early adopters, recommendation for you guys. Next slide. Next slide, please. Yeah, I'm interested in neuroscience too. So I just gave this as a recommendation for people who are into AI. Wow. So recommendation for guys into AI, we can only create a general AI if we understand how the brain works. As simple as that. It's not about deep learning. It has nothing to do with deep learning. I mean general artificial intelligence. I didn't mean problem specific. I mean general artificial intelligence. I will leave you with these thoughts and with this link. Next one, I believe next one is to tell you guys, but these are the organizations that I'm affiliated to. I lead these organizations. So, next one. Thank you.